Hi everyone, my name is Jennifer Walker. I'm an assistant professor at Rowan University in New Jersey in the US, and I'm going to be talking to you about spatiotemporal sea level modeling. So what do I mean when I say spatiotemporal modeling? We're beginning with a data set of high resolution relative sea level records. So we have some kind of proxy reconstructions that will be the input for our model. And it is important that they are fairly high resolution for the model to be able to work. And then we're using the spatiotemporal model to be able to analyze and quantify magnitudes and rates of relative sea level change, and then also specifically analyzing spatial and temporal sea level changes, hence the spatiotemporal modeling. So for this talk, I'm specifically going to be talking about the spatiotemporal empirical hierarchical model. So we have this input of observations with proxy reconstructions, and then it's using a hierarchical approach. So the model has basically nested levels that are working together to be able to analyze the data. And I'm going to be focusing on one model in particular that began with this paper, Capital 2016 in PNAS, as this was temperature-driven global sea level variability in the Common Era, where they produced the first global sea level curve for the past 3,000 years using this spatiotemporal model. And just for reference, this is a model that is run specifically in MATLAB. To use this model, the input, of course, first of all, is the proxy data, or the sea level reconstructions. So typically, this particular model has been used with a global database of Common Era proxy relative sea level reconstruction, so just focusing on the last 2,000 years. And this is a map showing where all the data is from, where you can see the data shown by the red dots. And there is a bit of a bias in the North Atlantic region, where there's a lot of data, especially from continuous salt marsh sediment cores, and then there's kind of more sporadic data throughout the rest of the globe. But it does cover about 36 regions around the world, and right now there are over 2,200 sea level data points in this database, but it's constantly being updated over time. The proxies that are used for the data within this database include foraminifera, diatoms, testate amoeba, coral microatolls, as well as archaeological evidence and sediment geochemistry. And the database setup is fairly simple, where it just includes the region, the specific site where the data is coming from, of course the reference, the proxy indicator, latitude, longitude, and then relative sea level in meters, and ages with their associated uncertainties. So we have the proxy data input, and then this model can also incorporate tide gauge data as well, so we have more information about the modern instrumental period. So specifically, we're including decadal average values from instrumental tide gauge records. This is data that's drawn into the model directly from the Permanent Service for Mean Sea Level, so you don't need to manipulate any of that data on your own, so it's pulling it in directly from that site. And there are a few criteria for the model to decide what tide gauges you're actually including. So shown here in green is what will be pulled into the model if we're using the global database of proxy records. So the tide gauges that are included are any that are longer than 150 years, and then any tide gauges either within a 5-degree distance of a proxy site and longer than 70 years, or is the nearest tide gauge to a proxy site that is longer than 20 years. So those criteria have to be fulfilled for the tide gauge to be pulled in from PSMSL. We also include the longer multi-century tide gauge records from Amsterdam, Kronstadt, and Stockholm, as they are also compiled by PSMSL. And we also include a global mean sea level reconstruction that was produced from tide gauge records from 1880 to 2010. So that was published by Hay et al. 2015. So that's incorporated into the model as well. So we have all of our input data from proxy data and tide gauge data. So now I'll go over essentially what the model structure is for the spatiotemporal, empirical, hierarchical model. There is a process level and a data level. The process level characterizes relative sea level over space and time, and then the data level links the relative sea level observations, those proxy reconstructions that we've input, to this RSL process. At the process level, we model the RSL field as the sum of 7 components. So mathematically, that's what this equation looks like here. And in this equation, x represents the geographic location, t represents time, and t naught is a reference time point, which we use the year 2000. So to go over these components, we have these fast and slow common global terms. So this is a term that's common to all of the sites in the database. And there are 2 temporal terms as fast and slow. There's a regional linear term, so that's constant through time. We have fast and slow regional nonlinear terms, and then we have fast and slow local terms. So we have these 2 temporal scales of this fast and slow term, and 3 spatial scales with the global, the regional, and the local. And I also want to note that for the regional linear term, we do use a prior mean with predictions from the ICE5G Earth ice model. So those are incorporated. So we have some prior information telling us about GIA for individual sites that goes into that regional linear term. Again, here because we're just talking about the Common Era or the last 2,000 years. So this is the process level. And then we have the data level. So that includes the relative sea level reconstructions with the observations from our database. So this is represented by this equation in the model where we have the relative sea level value at location x and time t. There's a site-specific vertical datum correction to ensure that all of the reconstructions are comparable to one another. We have the vertical uncertainty from our data, and then there's also an additional, the supplemental white noise term. So that's the relative sea level information, and then we have the time incorporated as well, so that the true age of each relative sea level observation just equals the mean estimate plus its error. So we have our process level of the model, we have the data level of the model, and the final component are the hyperparameters. So these are set through a maximum likelihood optimization to characterize the prior expectations of those spatial and temporal scales, as well as the amplitudes of relative sea level variability. So as I've said then, right, we have our nonlinear terms, which give us 3 spatial scales, the global, regional, and local, and the 2 temporal scales, which are the fast and slow terms. So with these hyperparameters, with all of these terms then, we can decompose relative sea level into different components, with a global component, a regional temporally linear one, regional nonlinear, and local. So as an example, this is what a table would look like of the optimized hyperparameters from the model, for example, using that global database. So we have all of our terms there, each having a prior standard deviation. We have our characteristic time scale in years. So our fast and slow terms are 11 and 356 years. And then a characteristic length scale in degrees that are set for the linear, the regional, and the local terms as well. So this is kind of the basic model structure in MATLAB, having this process level, data level, and setting these hyperparameters so we can set our spatial and temporal scales. So what we get with this model, for one, you can produce, as Capital 2016 did, a global sea level curve. So this is a signal that's common to all of the records in that Common Era database. From COPIDAL 2016, this is what those results looked like, where we have global sea level in centimeters on the left, and on the right we have the rate in millimeters per year and 60-year averages, both of these again over the Common Era. Now, as more analyses have been done using this model and more data has been added to the database, we've been able to update this global sea level curve since 2016. So there was an update with COPIDAL 2018, which is shown by the purple line. The original COP one is in blue. And then I updated this again in 2021 in one of my papers, which is the red line. So we found that as we've added more data to this database, there's been a bit of a smoothing of this global sea level curve over the Common Era, but we still see similar overall trends over this time period. We can produce a global sea level curve, and then the model also gives us the sea level data for each individual site. So I'll use an example here from northern New Jersey. So here we're looking at relative sea level in meters, here just over the last 1,000 years. The red boxes is our relative sea level reconstruction. The boxes are representing the vertical and chronological uncertainties. We also have tide gauge data plotted there with the blue line. And when this data was incorporated into the database, then with our model output, we get these spatiotemporal model predictions to fit the data from northern New Jersey. Now, something else this model can do then, although from this site we only had data for the last 1,000 years, there's a lot of other data available within the region at quite a high resolution. So we can get predictions for this site going back for all of the Common Era, even though we only had the proxy data at this particular site for the last 1,000 years. So here now we have magnitudes and rates of sea level change for northern New Jersey over the Common Era, because this was used with the entire global database, and there was a lot of other data from this region. So then we can say, for this particular site, from this model, we can quantify, for example, the rates of sea level change, where the rate was 1.3 millimeters per year from 0 to 1700, and increased to 2.1 millimeters per year from 1700 to present. So we can quantify relative sea level at individual sites like this, and then we also have the breakdown of individual components on different spatial scales. So for one, we get a regional linear component. So for northern New Jersey, that's around 1.3 millimeters per year. I'm not showing the graphs here because that's a constant. Then we also get the regional nonlinear component of relative sea level change. So this is the magnitudes and rates for northern New Jersey, just that regional nonlinear component. And then a local component as well, which is quite small for this particular site in northern New Jersey. So we have a breakdown using this spatiotemporal model with global sea level, and then these different regional linear, nonlinear, and local components for each individual site from our database. I want to give you an example then of another kind of further application to be able to use this model, specifically using this breakdown of components on different spatial scales, and that has to do with sea level budgets. So this is something that I did that was published in Nature Communications a few years ago, where I produced site-specific sea level budgets for 6 sites along the US Atlantic coast during the Common Era by separating each of the records into these process-related signals on different spatial scales. So continuing with our example from northern New Jersey, here we're looking at the Common Era. We have rates in millimeters per year. So the black dotted line is the total rate over the Common Era. And then we have this breakdown of these different components. So the largest, right, is that linear component in gray, driven by GIA. And then we have our global, regional, nonlinear, and local components as well. So we can look at individual time slices then, and I'll use the most recent century from 1900 to 2000 as an example, where you have your global, linear, regional, local, and then a total rate, and you can see how much relative sea level change was driven by each component. So in the last century, right, the global component has increased to nearly equal the linear component due to modern climate change, for example. So this is just another kind of further application as an example of what we can use this model for to produce sea level budgets. Now, everything I've talked about so far has been using the global database of proxy reconstructions as input into the model, but you can also use the spatiotemporal model for specific regions as well. And I'll just give two quick examples for how that would work. One from New Jersey. So some work that I did was just using a southern New Jersey sea level database as input into the model with regional tide gauges. So I think there were 5 or 6 tide gauge data that I used along with just proxy data from southern New Jersey. So then the nonlinear terms were characterized in this case by only 1 spatial scale and 2 temporal scales. So we went from using this equation with the 7 components with the global database to this simpler equation where we just have a global, or in this case, common to southern New Jersey component plus a linear term because we're just thinking about one fairly small region. And the idea is basically within the model, you would play around with different numbers of spatial and temporal scales to be able to maximize the log likelihood so you have the best model for your particular data set. So then we could look at just here data from southern New Jersey. This is also looking over a longer time period as well, over the last 5,000 years. And we have our data. There's some GIA models on this plot as well. And then in red is our spatiotemporal model predictions just for this southern New Jersey sea level data. As another example, using this model just for data from Singapore, in this case, we just use coral micro-atoll data from Singapore as well as tide gauges from Singapore. In this case, with this particular data set, the best model fit was to use 2 spatial scales and 2 temporal scales. So again, we're using a different equation to model the relative sea level field in that process level of the spatiotemporal model. And then as the figure shows in blue, that's our spatiotemporal model predictions using this coral micro-atoll and Singapore tide gauges as the only input data. So you can use entire global data sets down to particular regions to be able to quantify magnitudes and rates of sea level change, and then also look at these different components on different scales, depending on how large of a region you're looking at. So all of this code to be able to use this model is available online through Zenodo. So the most recent version of the code was published with one of my papers a couple years ago, where I used the model to look at the time of emergence of modern rates of sea level rise. And just for reference, the code has 14 main scripts to run where you can change the model setup and where you're setting up the scales to be able to optimize those hyperparameters. I typically run this model on a shared high performance computing cluster, and when I'm using the entire database, it takes about 4 to 6 hours to run. When I'm using those regional data sets, it's a lot less time, of course. I also want to mention that this code does have an updated framework called PaleoSTEM. So that's just Paleo Spatiotemporal Hierarchical Modeling. So it's just an updated framework for these modeling techniques that Yuqing Len put together, who was a postdoc at Rutgers. The code is all available already on GitHub. This is a preprint for a paper for this work, but the model has been moved to be able to be run in Python instead of MATLAB for this work. So that is an updated framework, a very similar setup, and to do the same kinds of analyses. And lastly, I just want to mention one other model, right? So a little bit different than the spatiotemporal hierarchical model. but this is work by Maeve Upton that came out last fall, where she's doing something similar where you have individual proxy sites and you can break down the relative sea level data into these individual components. So here she has a linear local, a nonlinear local, and regional component. So similar kinds of work, just that I want to mention, that's similar to these kinds of spatiotemporal modeling techniques. To conclude then, for these spatiotemporal sea level models, you have some kind of data input, whether it's instrumental and or proxy relative sea level data. The model structure is broken down into that process level, data level, and your hyperparameters that are set through maximum likelihood optimization. So you can quantify general relative sea level variability, producing a global sea level curve and looking at individual locations. And then you can also use the model to separate relative sea level records into these process-related signals on different spatial scales. And the model has applications for use with either global or regional data sets as well. So thank you for listening and hope to see you in one of the breakout sessions. Thank you.